All right, so this is the recipe for success on type 1 errors. And in this video, and by the way, welcome back, Mr. Sensei, the Stat Sensei. We're going to actually work through some AP problem on type 1 error. Now, I have the recipe of success that I used to use, and I highly recommend that you take a moment and read through this. I'll leave this on the screen for just a second so you can do that, and then I'll slide it up. I'm not going to read this to you. However, I will say that it contains a substantial amount of information that I think you'll find very useful. And the reason I'm not going to break it down is I have found that for actually running the test, the simplified version of the recipes tends to work better. And so, but this one probably has more information that's very useful that you need to know, but the simplified versions are probably better. So that's the recipe for type 1 error. And now we're going to look at the one for type 2. And I'm not going to break it down. I found the simplified version seems to work better, but there's a great deal of information that you need to know. So please make sure that you actually read all of this and make sure that you know it. It's in your notes spiral. And if you have questions about it, you can ask me in class. All right. Well, let's take a look at the simplified one because I am going to break that one down. So the very first thing is type 1 error, and all it says is measured by alpha, the probability of rejecting the null given the null is true. This is just a definition, right? And the purpose of this is you're going to need to refer to it. So that's the definition of type 1. Type 2, the probability of failing to reject the null given the null is false. And this is also just a definition. So first off, I got to tell you this, whenever they give you an FRQ and you're running a hypothesis test, if they don't ask you about what type of error is committed, you don't have to answer. So this is not you have to do from now on. This is when they ask you about errors, then you need to go about doing it. So the very first thing you need to do if they're asking about errors is either one of these two, and it depends on you and your preferences, whether you define the parameter first or write the null and alternative hypothesis. But regardless, you need to do that. Now, having said that, most of the time, if you're doing an FRQ, they're going to give you that information because they want to make sure that the answers are consistent across everybody. The next thing, you need to write the p-value down, whatever the p-value is. And a lot of times, they will give it to you. You won't even have to calculate it by running a hypothesis test because once again, they want to make the answers more consistent. But you may have to run the hypothesis test to actually get the p-value. Just depends on the question. So we basically have two situations. If the p-value is less than alpha, we're going to look at this column. And if the p-value is greater than alpha, we're going to look at this column. So we're going to first work all the way down to p-value less than alpha first. P-value less than alpha. If the p-value is less than alpha, our decision is going to be reject the null. And that's what we've done every time we've run a hypothesis test. However, if you reject the null, the only type of error that can be made is a type 1. Then you write the definition of it for a type 1 error, which we have at the top of the page, the probability of rejecting the null, given the fact that the null is in fact true. I highly recommend that you go through this, even though it's not required. Cross out the null. Why? Because we don't believe it. All right, so cross it out because we want to forget about it. And then circle the HA because we rejected the null and we believe this. And then our consequence, and we have to write this out, we believed the alternative and did whatever based on our scenario, but that was an error and the consequence is this. Now, I'm going to tell you, this is a guideline. This is not a word-for-word template. Can't give you one for these. Like to, but can't. All right. So, but make sure we'll tell what you did, tell what you believed, then what they did, and what the consequence was for that. On the other hand, if the p-value were greater than alpha, we would fail to reject the null. All right. And if we fail to reject a null, the only type of error that can be made is a type 2. Doesn't mean we did commit a type 2 error, but the only type that could have been committed was type Then the next thing you're going to need to do is you're going to need to write the definition of type 2, which is the probability of failing to reject a null given the fact that the null is true. All right. In this case, you're going to circle the null hypothesis and you're going to cross out the alternative because we believe this. In this case, we're believing this, but we're not believing that. Consequence, we believe the null, and make sure you put it in context as what it is you're believing. And as a result, we did this, but it was an error, and the consequence of what that was is that this. Once again, this is a guideline. This is not a word for word template, okay? And then at the very bottom down here, I have, if they ask about p-values, we've talked about it before, but real quickly, write the null and alternative if you haven't already. Make sure the parameters defined. And once again, the order on this doesn't matter that much. Then you define the p-value in context. Please take a moment to always define these things, whether it's an error or anything, because if you tell them that you know what it is, it's just a good start. So p-value is the probability of getting a test statistic as extreme or more extreme given the null is true. Technically, giving them the definition gets you no credit, but it sets the reader up for letting them know that you understand what you're talking about. And then there's a blank percent, whatever our p-value is, that we would get a test statistic, this extreme, in favor of the alternative in words, when in fact the null in words is actually true. So let's look at a problem. And I'm going to kind of move through this problem a little bit fast. So you're probably going to have to stop the video to write down all of the, to write everything down. Okay. So this problem was taken from 2008 of Form B, question 4, and it's been modified a bit. So a researcher wants to conduct a study to test whether listening to soothing music for 20 minutes helps reduce diastolic blood pressure in patients with high blood pressure compared to simply sitting in a noise-free environment for 20 minutes. 100 patients with high blood pressure at a large medical clinic are available to participate in the study. Propose the design for the study to compare these two treatments. We actually did that part of the problem a long time ago. All right, so, and here's what we'd say for part A. Write the name of 100 volunteers on 100 individual pieces of paper, place the slips in a bin and mix thoroughly. Draw 50 names without replacement. The first 50 names will be assigned to listening to soothing music for 20 minutes. The remaining 50 patients will sit quietly in a noise-free environment. Prior to administering the treatment, the diastolic blood pressure will be measured for each volunteer. After 20-minute treatment has passed, the patients will again measure their diastolic pressure and compare pressures pre minus post. And you always need to give your order to determine which treatment resulted in the greatest decrease in diastolic blood pressure. And that's what we've done before. And you're like, Stat Sensei, why? This is not about errors. I know it's not, but this is what that problem started with. Then part B, we start getting into errors. The null hypothesis for this study is that there is no difference in the mean reduction of diastolic blood pressure for the two treatments. And the alternative hypothesis is that the mean reduction in diastolic blood pressure is greater for the music treatment. Now, I want to tell you, we need to be very careful. Paired tests would be written like this, mu D equals 0. But this isn't paired because they're not being tested twice. And there's not a natural pairing. So this is not what this is talking about. We actually have two separate groups, one sitting in a quiet room and one is listening to music. So in this case, we have a null hypothesis where we could say mu1 equals mu2, or we could say mu1 minus mu2 equals 0. And basically, these are saying the same thing, just a little bit of algebraic manipulation. But it's nice saying this looks like equals 0 because it looks similar to that. But we have two groups. We have the average of the group listening to music and the average of the group sitting quietly. So the null is that there is no difference between the mean reduction of diastolic pressure. If the null hypothesis is rejected, well, if we reject, that means we had a small p-value, and the only type of error we could have committed is a type 1. The clinic will offer this music therapy as a free service to their patients with high blood pressures. Describe a type 1 error. They're saying, hey, we rejected, so the only one you could have done is a type 1 and the consequence in the study. Well, here we have mu1 equals mu2, and that's what we said with the recipe. Start off by writing the null, all right, an alternative. Then we need to define the parameters in context. Let mu1 equal the true population mean for diastolic blood pressure drop for those listening to music. Mu2, the mean diastolic blood pressure for those dropping for those sitting in a quiet room. So the drop is greater than those in a quiet room. A type 1 error is mistakenly rejecting the null when it's in fact true. Because that was the next thing it said do, write the definition for a type 1 error. What would happen in this? Oh, and by the way, so we made a type 1 error. So a type 1 error says, you know what? We rejected this, but we believe this, but this was true. All right. In this case, we mistakenly believed that listening to music would have a greater impact on lowering diastolic blood pressure than sitting in a quiet room, when in fact, it did not. As a result, the clinic would be providing and paying for treatment for patients that wasn't any more effective than sitting in a quiet room. Your situation, what you write might be slightly different. That's kind of what they're looking for. A p-value of 0.0017 is calculated. That's a small p-value, and against most typical alphas is going to be rejected. Explain the meaning of the p-value in context and explain what type of error may have been committed. P-value is the probability of getting a test statistic as extreme or more extreme given that the null is true. Guess what? We already wrote the null and alternative above. We've defined the parameter above. Now we've defined p-value. Okay, so we just defined the p-value. Now we need to put it in context. There is a blank percent chance. There is a 0.17% chance that we would get a test statistic this extreme in favor of music. This is coming from our alternative, having a greater reduction in diastolic blood pressure than sitting in a quiet room, when in fact the two treatments are equal in their effectiveness. And the reason we said that is and then we had to say, justify what type of error we would have made. A p-value of 0.0017 is less than alpha 0.05. Thus, we would have rejected the null. If we reject the null, the only type of error that we could have committed is a type 1 error. All right, I appreciate you listening and watching. This will be type 1 error. The next video will be on type 2 errors. Thank you.